parameters that you have to consider. Again, as I said, it's not more difficult. Okay, you won't see anything new. The only thing you see new is the equivalent length. Okay, right. So from here, an aluminum column of length L, and we have a rectangular cross section that has a fixed end B. So B is fixed and support a centric load at point A. You can see at point A, there's a central load P. Two smooth and rounded fixed plates, okay, restrain NA from moving in one of the vertical planes of symmetry of the column, but it is allowed to move in the other plane. Okay, so this is the part that we are not sure now. Okay, so too smooth. Okay, right. We are going to determine the AB ratio of the two sides of the cross section corresponding to the most efficient. Okay, down here again, it write the most efficient design against buckling. Okay. Then the next part is we are going to put numbers in. Design the most efficient cross section of the column, knowing that the length is in 20 inches. The Young modulus is 10.1 times 10 to the power 6 psi. The load given is 5 kilopounds. And we are required to use a safety factor of 2.5. Okay, so that is what we are given. Yeah. Okay. So the thing now that comes to our mind, okay, is most efficient design against the buckling. Okay. What do we mean by most efficient design? Okay. Before we go any further, we know that we have critical load, right? And this is equal to pi squared EI over LE squared. Okay. Very easy. Formula is so straightforward. Okay. So what I'm going to do next, okay, what we are going to do next is we are going to sketch. Okay, we're going to sketch so-called like a free body diagram. Okay, so-called like a free body diagram. So you guys can see the image. So the first one I would like to consider. I'll draw up my transformation first. Okay, so we are going to follow the transformation line. The question. This is our x. This over here is our z, and this over here is our y. Okay. So the first thing that I want to focus on is we are going to look on buckling. Okay. And this plane over here, we are going to call our XY plane. Okay. So now I'm going to sketch how it looks like on the XY plane. Okay. So we have something like this. It says that at point A, that this is rounded and it is smooth. It deliberately highlight it is smooth. Then we have our beam. Okay, yeah, it looks like this. And then we highlight that, and it highlight it as smooth. Okay, and then I'm going to draw the geometric centroid. So as I said before, we are focusing on the XY plane. Okay, we have a load over here that is P, and at the other end, it is fixed. Okay, at the other end, it is fixed. Okay. Now, what they highlight is this is they deliberately highlight that this is what? Smooth and rounded. Okay. So if we were to call this our point A, our point B, we know at point B, by looking at this, we know that moment is not equal to 0. Okay. And we know that this is going to be what? Fixed. On the other hand, when it says smooth and rounded, we know m is equal to 0. Okay, when m is equal to 0, theta is not equal to 0 now. So this end is as good as it is pinned. Why is pinned? Because there is resistance on the left and right that prevent it to move. I think I better prevent it to move about the y-axis. Okay, so if I'm going to sketch out transformation, this is our x, and this is our y. Okay, and there's a resistance in I'll call this Fy. Okay, there's a resistance force. Okay, so that is for this reason, one end is fixed, the other end is pinned. Now I'm going to step away for a bit. Okay, now what if now at point A? Okay, what if now at point A it is no more round, but rather than round, it becomes what? It becomes a rectangle, like this, right? So when this is the case, right, you can see the difference now, right? You can see the difference. One is round, okay? And then we still have our load coming down. So this is our geometric centroid, and over here, this is our P. Okay, now point B, the condition did not change, it's still the same. Okay, so I'm going to put here fixed, I explained to you earlier. Now at point A, because this is flat and this over here is also flat, now M is not equal to what? 0. When that's the case, this is how both ends fix. Okay, because the vertical section is preventing the what? The rotation. To prevent a rotation, you need to have an acting moment. That's why moment is not equal to what? 0. Okay, so for this reason, that's why we have to be very, very careful. For this reason, right, they highlight that what? At point A, we have two smooth and rounded fixed plate. Okay, they highlight that it's rounded and the fixed plate. When that's the case, when you remove the support at B, the entire structure can swing left and right. When that's the case, it is the resistance to moment is equal to 0. The example below, okay, is rectangular, is flat. Okay, the structure only can go up and down. It cannot go left or right, and it cannot what? Rotate. So this is how the fixed end will look like. Are we clear? Okay, so if I were to in your term test, I were to change the condition, at least you have an impression what is going on, what will happen when it's round, and what happened when it's not round. Okay, right. So that is for the xy plane. Okay, so for the xy plane, we know that one end is pin. So one end is pin, and the other one is what? Fixed. So we look at our table, one end pin and one end fixed. So this is the one. Okay. So this is exactly what is going on, right? For the condition that we have, one end pin and then one end fixed. So therefore, LE is equal to 0.7 L. Okay. So now we calculate our equivalent length. Okay. Now, next we are going to look at a different plane now. Okay, we're going to look at a different plane. So what I will do is I will bear with me. Okay, I'll move this away. I want to do it side by side so that you can see it better. Right. So the next one, right, is now it's a different axis now. Okay. So now what I want to do now, okay, I want to I put this on the box. This is just to show you how is fixed and fixed look like. Okay, not necessary. Sorry, not necessarily related to the problem that we have, and I don't want you to be confused. Put this in a box. Right. So the next one we are going to look at is we are going to look at. We're going to do this in a different plane now. So we have already done the XY plane. Now we are going to do the next plane. Okay. So the plane that we're going to look at is going to be our XZ plane. Okay. So our XZ plane, so I'm going to sketch out our XZ plane now. So the XZ plane looks like this now. Okay. And this is our point B. This is our point A. And then we have so-called the fixed part over here. Okay, there's the fixed part. Okay. So now I'm going to draw the centroid. Okay. And then we have a load over here, P. So I'm going to again sketch our transformation. This is our X, and this is our Z. And what we realize there is the structure has no resistance about or no restriction or no motion restriction about the z-axis. So when this thing deforms, or when buckling going to occur, it's going to be buckling this way. And this is where your P is, right? Why? Because you